Let's continue in this video with the equilibrium of this infinitesimal cube. So we were talking in the last video that we could take advantage of doing this rotation and translation equilibrium relations. And I also mentioned that we could benefit from it by reducing, or it's going to allow us to simplify the number of apparent incognitas or unknowns that we have in the problem. Let's start by defining the rotation equilibrium. I believe this is one of the most interesting ones, rotation equilibrium. To this, I'm going to draw a cube, and the main idea of the rotation equilibrium is to propose that all the sum of all moments of the moments caused by the forces applied to the cube are 0, 0. And I will I will draw here the cube or a cube. And what I will do this time is to calculate moments in this cube around, let me draw this a little bit better, and hidden lines. I will draw an axis. I'm going to suppose that the x-axis goes through in the middle, or through the cube in the middle of these faces. This is the x-axis. And if I look the x-axis from this side here, I'm going to consider that the moment is going to be positive if it turns the cube counterclockwise in this direction. I can draw this eye a little bit better. Something like this. Well, I don't know if it's better, but I don't know, you understand. This is an eye. I'm watching this from this side, this one here. And whatever force makes the cube rotate anti-clockwise, I'm going to consider that that's going to be a positive moment. To this case, and seeing the stresses drawn in this first cube that we draw when defining the indices notation and the positive convention here. So I'm going to draw only those stresses that are going to produce or being produced by forces that make the cube rotate around the x-axis. They're going to be like something like this. I'm going to start by the top. In the upper face, I will have tau yz. This lateral face, I will have tau. This is on the z face, zy. In this negative phase in the back, I will have shear stress tau zy. And the bottom phase, I will have tau yz. These are the only stresses caused by forces that makes that cube rotate around the x-axis. Notice that on purpose, I have located the x-axis in the middle of the cube or through the middle of the cube. So I can disregard the effect of, for example, the normal stresses around any of the, or located in any of the faces. Well, in this case, if I propose the kind of the condition that all moments have to be, or the sum of moments have to be equal to 0, what's going to happen is as follows. First, to start writing here, we'll try to simplify this. How can I hide this? It was fine. So to hide it again. Okay, perfect. I know that, for example, let's take one of them. Let's take tau yz. Tau yz makes the cube rotate anti-clockwise, meaning that the tau z is produced by a force that makes the cube rotate in the positive direction, or is going to produce a positive moment. Then I'm going to write that tau yz. Then this is a stress, but I need to transform this into a force. To transform this into a force, I need to know an additional information. There's going to be the dimensions of, let me use this one, the dimensions of the cube. I'm going to say that this is going to be, or this cube is going to have a dimension in x, dx, dimension in y, dy, and a dimension in z, dz. Now, by knowing this, I know that this shear stress is acting on a phase which dimensions are dz times dx. Coming back to here, tau, the shear stress tau yx multiplied by dx times dz. This is going to represent the force. The force caused by that stress, or the stress caused by that force, or the force that caused that shear stress. Having this, or knowing that this is the force, I need to know also the arm in which I could apply the moment. And I know that the arm is going to be half of the y distance, and that's going to be represented by dy over 2. If I look a little bit better, or not better, if I look with detail the cube, I know that also that this shear stress here, tau yz, the one represented in the negative phase, is also, by our convention, a positive shear stress. It's going to make my cube rotate in the positive direction. Meaning that I could do this. So I could add a 2 here to represent that these two forces, or these two stresses, tau xy, yz, and on the top in the positive phase, and tau yz in the negative phase, they form a couple or a pair of forces, and that pair of forces is going to produce a moment around the z-axis, and that's going to represent it with these two here. Similarly, I can do the same with the tau zy, meaning that I could say tau zy, I understand that it's going to rotate this cube clockwise, and that's going to be a negative moment. So I would have to subtract here twice, or 2 times, shear stress zy. The area where this shear stress is applied is in the phase, or the phases are represented by, or this area is represented by dx times dy, dx times dy, and the arm of the force, or the length of the force to the rotation axis is half dz, or dc divided by 2, and this has to be equal to 0. This here is another force. I can see now that evidently I could get rid of these 2. I could get rid of these differentials here, because when I put this term in one side of the equation, and I put this other term in the other side of the equation, this is going to kind of cancel out one to one. I'm going to end up saying that the shear stress, let me change the color here. Shear stress yz equals shear stress cy. This is done in the x-axis. I invite you to do the same with the other axis, because it's going to happen that, and believe me in this, you can do it proposing axis, for example, or another axis that goes in this direction, meaning that this is aligned with the z-axis. And what you're going to obtain is something very similar to what I have obtained here. That in the y-axis, you're going to find that y-axis is represented by this one here. Where is it located? Y is x, yeah. Yeah. Tau xy equals to tau yx, and in z, that tau xz equals to tau zx. Yes. This is what is called, this relationship that we have found in here by doing or by utilizing the rotation equilibrium is what is called reciprocity of shear stresses. I'm going to write it down here. These relationships are called reciprocity of shear stresses. This is going to allow us to, as I mentioned, to simplify a lot of our formulations and calculations that we will be doing in the future. Keep in mind this. Whenever you see a term like, tau yz is going to be equal to y to tau zy. However, it's important to keep in mind that the indices are very important to determine where that stress is applied, on which phase is applied, and if that stress is positive or negative. Respectively, that we now are saying that those stresses are the same, obviously, but it is important to keep in mind that we have to somehow respect the writing nomenclature of this. Now, when we jump to put a little bit up, get this down more. Now let's talk about the translation equilibrium. Translation equilibrium. This is also going to bring us very interesting relationships, something that as a question of equilibrium is going to allow us to determine body forces, or if we're talking about rigid body motion, it might allow us to calculate some inertia terms due to the acceleration of the body. But in this case, we are not, in this course, we're not applying that, as I mentioned before. In the translation equilibrium, I'm going to see just one phase. So I want to treat this as a first as a two-dimensional case to explain something, but instead of doing that right away, let me just draw again a cube and some of the stresses on the cube to explain something that is called kind of the different, let's say, how different are the stresses between one point and another. So in this case, I have written that this stress here, tau sigma xx, this is the normal stress in the x phase, is going to be equal to the normal stress represented in this phase. However, that's not completely true, or not in all cases that happens. There is always a difference between this stress presenting here and this stress presented here. And that difference is going to being caused by a differential, because the stress is going to vary from this point of the cube to this point of the cube. To explain better that, I will draw another cube, as I mentioned, but I won't draw the whole set of stresses that are represented in this cube. The cube, the hidden lines to represent the negative phases, coordinate axis Cartesian axis x, y, and z. And let me represent here first in the negative phase, normal stress sigma xx. That's what we had before. And I'm going to represent just a couple of sides, or yeah, let's take just the x phases. I will have also, as according to the way we oriented these shear stresses, I will have this tau xy, and I will have also tau xz. Now, if I come to the positive phase, we'll try to demark this as the negative phase. Then the positive phase, this one here. In here, I will have normal stress, but it's not going to be the same magnitude as in the negative phase here. It's going to be plus something, an increment. Let's call it that it's going to be an increment. It's going to be a differential of normal stress xx. So I have in here the normal stress x sigma xx in the negative x phase, but then well, it goes in the infinitesimal cube to the other end. It is incremented by a small magnitude or a small quantity called a differential of this normal stress xx. I'm going to get rid of this and this. In the case of the shear stresses, it's going to happen the same. I will have this shear stress is going to be tau xy plus a differential, a little bit more, something called d tau xy. Similarly, I'm going to have here tau xz plus a differential, tau xz. Please notice that I have just drawn this in two phases, but this is going to happen in all of the phases that I have in the cube. So these positive phases, this positive phase here, and this negative phase, and this other negative phase here. I'm going to have the same. So if I wanted to draw the same in one other phase just for, by the way, these are called phases, or you can call it facets. Some authors call it facets, but I'm going to draw another one just for the sole purpose of explaining how the thing goes. Let's imagine this one, this negative phase here is going to have the sigma zz, but also I will have here the shear stresses. These shear stresses are going to be this one. Let me put it also segmented. And downwards. This is going to be tau zx, just that one. And this is a small mess here. I shouldn't have. And trying to fix this. So this is the line, and this is this. Try to bring this here. Z, Y. Now in the positive phase, I'm going to have then, this is going to be, let's imagine that what I'm going to write next is going to be represented in this phase here. It's going to be sigma zz, and it's going to be a positive tau, sigma zz plus something else, tau zy plus something, variation, and this one here, tau cx plus a variation. Heads up, this is represented in here, or this corresponds to this phase here. Then the interesting question is to ask us, how much is that variation? Is it, at this moment, it's not important for us to know if it's negative or positive, a positive variation, but just to know how much is that variation. So we're going to assume that this variation is positive. So it's going to increment, it's going to increase the value of the, in this case, if I'm thinking about the normal stress in the X phase, it's going to increase the value of this normal stress. So you're going to find in the textbooks that there it is mentioned that using something called Taylor series expansion, you can represent the variation from one point to another. Meaning, let me draw something that's going to help us to understand this. If I look at this from the Z phase, kind of like this, I'm going to imagine that I'm going to have one part of the cube. In this part of the cube, seeing it from this point of view, I'm going to have in here the normal stress in the X direction. And actually, let me write it better. This here, this magnitude here, is going to be normal stress as the same as this one. However, as we mentioned that the stress is increasing from one phase from the negative phase to the positive phase, I'm going to have one small piece here. The scale is not important here. There is going to be this increment, the increment that I'm looking for. So it's going to start from this point here, and it's going to increment to this point here. Bringing also the same dimensions of the cube that we have used before, I'm going to say that this dimension here is dx. How to estimate then the value of this differential of stress? This is going to be valid also for shear stresses. One interesting thing to try to find out here is the slope of this curve, this one here. If I find the slope of this curve, then I can multiply the slope of this curve times this longitude here and with this length. And I could then, with the length, I could determine how much is this piece here in this kind of the increment here. I understand that, or I can say that if I consider that there is an angle alpha here, and I apply the tangent to find out the value of that alpha angle. So I can say that tangent of alpha equals to this small piece here. There is a differential of the normal stress divided by the length, dx. Coming from the geometrical properties of the line, I know that this is also equivalent to the slope of that line that we're representing there. And if this is the slope, then I can use this value here to calculate how much is this one here. How to do that? I just say that this increment here, the derivative of this normal stress is equal to the slope. Sorry, I need to change this. As this magnitude can change also, meaning that this term here can change in terms of x or y or z. I need to represent this as a partial derivative here. Then this increment here is going to be equal to the slope. There is partial derivative of sigma xx divided by partial derivative of the x, of x, of sigma x. Let me go back. partial derivative, let me mark it here, of normal stress divided by partial derivative of x times dx. This is going to be a general representation of these increments in each one of the stresses presented on the cube. It doesn't matter if it's a normal stress or a shear stress, it's always going to be represented in this fashion. For example, the increment in the shear stress xy is going to be equal to partial of this tau xy divided by the x times dx. And so on. Let's make also the tau y xz, the increment or this differential of tau xz equals to the partial of tau xz divided by partial of x delta x, or dx, differential of x here. Good. What's next? Next, I need to move this from here. Put it down. A little bit more, maybe. Yes. Now having this, I'm able to formulate the translation equilibrium by assuming or by proposing that the sum of forces is going to be equal to 0. And we're going to follow the convention that anything that is aligned with the positive axis of our Cartesian coordinate system is going to be positive and negative otherwise. Let's start, or should I draw another cube to make it better? Maybe not. Maybe not. Okay, let's start. I have to put it that everything is seen. But let me move this one here. Put here. This is what we're going to do. Nope. Get rid of that. This is what we're going to do. Yes. Let's do, so it's going to be complicated to do the 3 axes at the same time. So let's do just one axis. Let's do the x-axis. And yes, I think it is convenient to draw another cube representing the stresses that are affecting or influencing the x-axis or acting on the x-axis. I will draw it again. We'll draw that cube. Try to make it a little bit bigger. 6. Deviate it a little bit, but this one. Yes. Come back here, then the hidden lines. I'm interested only in the x-axis. So I'm going to represent, I said, I'm going to draw the stresses that are acting on the x-axis only. I'm going to use red for the positive directions, and I'm going to use blue to draw the negative stresses. These ones are going to be here. Let's start with this positive phase here. Actually, let me finish drawing this Cartesian axis, z and y. I will have normal stress in x direction plus, we said that this is going to have an increment that is going to be xx divided by partial x times dx. Another one who is going to be appearing is contraposition of this normal stress vector, this one here. I will have also on the top face a vector which is, let me draw it away from it or write it away from it, tau y x times an increment, and that increment is going to be partial of tau yx divided by partial of y times dy. Then in this lateral face, this one here, I will have another vector. I will write it also away from it. It's going to be tau zx plus an increment, and that increment is going to be partial of tau zx divided by partial derivative of z times dz. Other negative stresses have to be written there also. In the bottom face, in here, this one here, I'm going to have this shear stress, and this one is going to be tau yx. And the last one is going to be in this other face, the opposite face, the one that is behind everything, this one here. And this is going to be tau cx, zx. Yes, these are all the stresses acting on the x-axis. Now, to formulate the translation equilibrium, I need to make the sum of these vectors. And again, positive vectors are those aligned with the positive Cartesian axis, and negative are those aligned with the negative Cartesian axis. Let's keep moving this downwards because we don't need yet this. Good. Let's start our sum of vectors here. Let's start representing the positive ones. So sigma xx times, plus the increment. Again, we're talking about forces, and forces, to convert these stresses into forces, I need to multiply the stresses times the area where those stresses are applied. To make it sure, so let's say this is dx, or this distance here is dx. This height here is going to be dy, and this deepness here is going to be dz. Then this normal vector, normal stress here is applied on this face that I'm presenting here, and this face has dimensions dy times dz. I will write it again here, dy times dz. I'm going to subtract now the opposite side, which is this one here, minus sigma xx. It is also applied on an area which dimensions are dy times dz. Let's continue. Plus, let's take, for example, tau yx, this one here. Then tau yx plus the increment, this one here. Then the area where this shear stress is applied has dimensions dx times dz. Minus its opposite, this one. Yeah. Another one, or the last one. I'm going to write down here. Plus, I will have tau zx plus the increment the partial of tau zx divided by dz times, or partial z times dz, multiplied by the area where this stress is applied, and the dimensions of that area is dx, are dx times dy. Let me write that y better. I'm a mess with this font. Minus the complement. This t cx. Again, zx is acting on a phase which dimensions are dx times dy, dx times dy, and this is going to be equal to 0. Now let's take a bunch of things out of those parentheses and let's make the subtraction or simplifications needed to get to a better or nicer looking conclusion. Let's start analyzing this. Right, something that I missed here was that this stress, you mark it here, I need to multiply it by the area where the stress is applied. And that area is going to be the bottom face of the cube. And the area of that bottom face is going to be dx times dz. Dx times dz. All right. Now I am ready to start simplifying this long equation. First, I will extract everything from the parentheses. Basically, these two terms. And let's see how it looks like. Well, three terms. And let's see how it looks like. We put a division here. I'm going to have sigma x times dy dz plus the variation, which is represented by this term here, dx dy dz minus sigma x dy dz plus tau yx, and it dx dz perfect plus variation yx. Try to write it better because it is confusing. Yx divided by partial y. All right, and that's going to be multiplied times dx dy dz. Great. Then I'm going to have minus tau yx dx dz plus tau zx dx dy plus the variation cx z. Right. Yeah. This is the z minus tau zx dx dy equal to 0. Right away, you can see that we have at least three terms that we can get rid of right away. This is the first one that is repeated. Then we have the second one here. And then we have this third one, where is located? Variation. Yeah, is it this one? Yeah. Yeah. So we have the individual terms, those that are not the variation. So we're left with this one. We're left with this one here. This one. Yes, and we're left with this one. Yeah, 1, 2, and 3 terms. Just bear with me. All right, let me rewrite this equation. This is going to be delta sigma x divided by delta, not delta, partial x multiplied by dx dy dz plus partial of tau yx y times dx dy dz plus this last variation dz dx dy dz equal to 0. Because we're working with this cube and this cube has these 3 dimensions, we can guarantee that none of these elements here is going to be 0. Then I can simply rewrite the equation as this one here plus this other variation plus the last one, tau z x divided by partial z. Because I can move this, and this to this side. And this is going to be equal to 0. I could include the force, the body force, in this equation of equilibrium if I had considered it before, and it would look something like this. It would be the same result as we have it here, plus the tau yx divided by dy plus the tau zx divided by z plus body force in x equal to 0. This is a way we could do it. Actually, let's write it in that fashion. The same we did here with the x-axis, assuming equilibrium, that all the forces, the sum of forces is equal to 0 along this x-axis. We can do the same with the y-axis and the z-axis. And as I mentioned, this procedure is going to be identical. Then what I'm going to do is I'm going to write just the results of this procedure at once. So I'm not going to repeat the procedure again, as I mentioned before. We're going to end up with this series of what is called equations of equilibrium. And that's going to be, let's include the body force in this one. It's going to be this one here, plus, again, I don't know how many times I have written these equations, but to get used to it, dz plus body force in x equal to 0. This is in the x direction. Let's do the same for the y direction. This is going to be the variation of these ones here plus variation of normal stress plus the variation of this shear stress plus body force equal to 0. This is in the y direction. Then to move this downwards. Along the z direction, we're going to have this variation xz dx plus tau yz dy plus the normal stress, the variation of the normal stress, plus body force in the z direction equal to 0. Again, these 3 equations form what I have just called the equations of equilibrium. Then it is important to come back and say that thanks to the rotation equilibrium, we found out something called the reciprocity of shear stresses, where the indices are change positions, and it means that no matter how you write them, the indices are the same. So, or not the shear stress is the same, but it's important to keep in mind that we have to write correctly the indices so we can position or know where these shear stresses are applied on the cube. But this gives us that these stresses are equal, are equivalent. And from the translation equilibrium, we get the equations of equilibrium for the cube. And this is going to allow us to determine if the part of certain parts of the insides of the body are in equilibrium. Also, it would help us to determine, for example, what are the body forces applied due to the stresses, or resultant body forces applied due to the stresses, or in the other way around, what body forces are applied so it's causing these stresses here presented. I'm going to stop the video right now, and then in the next video I will talk about what happens when this cube that we have studied already is not oriented with the Cartesian coordinate system. We see here in this cube that the faces are perpendicular or parallel to certain planes in the Cartesian coordinate system, but what happens when this is rotated? And that's what we're going to take a look at the next video. And for that, we're going to discuss how to describe orientations in space, and we will use for that something called the direction cosines. So thanks for watching, and see you or talk to you in the next video. Thanks.